Good morning, everybody. First thing I wanted to bring up today was the first essay exam, which I believe is due very soon, maybe tomorrow. Yeah, it is tomorrow, right? Yeah. So actually, I hadn't addressed in the lectures the last question, the 10th question that hasn't been covered. Yeah, so I'm going to cover that. This morning we've fallen a little bit behind in the course of the semester because I like to go on and on. We've fallen a little behind. I hope to start on the topic of identity at some point today, though. But first I want to talk about the problem raised in that 10th question. So I don't know if that's going to make an issue for anybody. So what I'm going to do anyway is extend the deadline for the first essay exam to Monday at 9 a.m. 9 p.m. Monday 9 p.m. So everything's always due at 9 p.m. So yeah, Monday 9 p.m. So I'll give you some more time to deal with that since we're just getting to that today and really just finishing up the unit today. So it's not really, shouldn't have the exam, like do the next day after the exam. Okay, so is that agreeable with everyone? No dissenting? Yeah, so that would give you the weekend. I'll give you a bunch more days. So you can have a more polished product in any event. All right, so this last thing I wanted to talk about is actually a problem that the nominalist can raise against the realist. It has to do with, I guess, going back to the formal cause argument, there was this sort of tacit or implicit assumption on the part of the realist that for any kind, like cat or dog or whatever, there's going to be a quality in virtue of which all the members of that kind belong to that kind. So for example, Rover, Fido, and Spot all belong to the kind dog because it's because and therefore is explained by the fact that they share a common quality, in that case, the quality of dogness or canininity, or the property of being a dog. These are all ways of talking about the same shareable abstract quality. It turns out, though, that you can prove that the assumption put in that broad way can't possibly be true. It can't be true that for any kind there's going to be a shared quality that all the members of that kind have. It may be true in many cases, but it can't always be true. And that would be a strike, some kind of strike against the realist argument. So it's not going to be the case that you can always explain group membership by a shared group property. There will be some cases where that fails, as I will demonstrate. That doesn't necessarily mean, as we'll see, that the realist has to give up the formal cause argument, but would have to be understood that it only applies in certain cases, which is okay. I mean, the argument originally just put forward for dogs. There's no problem with the kind dog, or the kind cat, or the kind table, or the kind red or square, or any of those kinds. It's some fairly odd kinds that turns out can't have any shareable group property because of the logical paradoxes that would result from saying that there is such a property. And this sort of goes back to the famous argument that took place between Bertrand Russell and Gottlob Frege, having to do with the foundations of mathematics back in the very early 20th century. And in that context, it took place in terms of set theory, where there was a similar assumption, which is that for any specifiable group of things, there's going to be a set corresponding to that group. So if you have a predicate which applies to a number of different things, then there would have to be a set, a unique set of objects in existence to which that predicate applies. Frege had made that assumption in developing a framework for the foundations of mathematics, and then Russell discovered one day that it led to a paradox and that there couldn't be such a set. So looking at it in terms of sets and not in terms of properties, the problem that Russell found was that there are some things, there are some sets that are members of themselves and other sets that are not members of themselves. So just to say, take the empty set. Obviously, that's not a member of itself, right? It doesn't have any members. So, right? From that, we can see that it's not a member of itself. So a set would be a member of itself if and only if among the elements in that set would be the set itself. So what kind of set could look like that? Well, the set of all sets, for example, right? So if you have a set, right, some really big set that contains all sets, right, that set would also have to contain itself as a member. This is a set of every set, and it's a set. So the set of all sets. So if you go by Frege's principle, there ought to be such a set. It would be, I guess, infinitely big or something, it would seem. And among its members would be itself, right? So it would contain itself. So some sets have themselves as members and other sets don't. So there's a distinction that can be drawn between two types of sets. You could see parallel distinctions, say, for predicates. Some predicates are self-applicable and other predicates are not self-applicable. So some predicates can be predicated of that predicate and other predicates can't. So how about the predicate cat? Is that predicate applicable to the predicate cat? Is the predicate cat a cat? No. Right, so that would be a case where the predicate doesn't apply to itself. But you can think of other cases where it would apply to itself. Anyone think of an example like that? A predicate which can be applied to itself. The predicate English, right? Right, E-N-G-L-I-S-H is itself English. It's not French or German or Japanese or something. So that would be a self-applicable predicate. So that's sort of parallel to this idea. So in all these kinds of cases, you're going to wind up getting paradoxes for certain types of predicates, or in this case, sets. So the famous theory, so the example that Russell came up with that showed that if you just have this unrestricted principle that there's going to be a set for any group of things which you can describe by some predicate. He concocted this set. It's the set of all and only those sets that are not members of themselves. So remember, some sets are members of themselves and some are not. So now consider the set, which is the set of all and only those sets that are not members of themselves. So I'll write that out. The set of all and only those sets that are not members of themselves, like the empty set's not a member of itself. And lots of sets aren't members of themselves, right? Like the set of dogs, right? wouldn't be a member of itself because it's not a dog, right? The set of all dogs. So the set of all dogs has got Rover, Fido, and Spot, and all the other dogs, but it doesn't have as one of its elements itself, namely that set. It's not in there with Rover, Fido, and Spot because it's not a dog. And the definition of the set is that it contains all and only dogs. All the dogs and nothing else. Right? So the set of all and only those sets that are not members of themselves. And we know there are lots of sets like that. The set of dogs, the set of cats, set of apples, of tables, the empty set. All of these are sets that are not members of themselves. So you'd think then that this should be the set that contains all and only those sets, right, that are not members of themselves. It would have the set of dogs in it, and the set of cats, and the set of tables, and the empty set, right? The set that contains all those sets would be in there. Okay, so Russell proved that this set, that it's logically impossible for this set to exist. So how would that argument go? Well, either this set is a member of itself, or it's not the case that this set is a member of itself. Right? By the law of excluded middle. Either it's raining or not. Right? So either the set is an element of itself or not. So now you take each horn of that disjunction and you show that it leads to a certain result, and that result is going to be impossible. So suppose, for the sake of argument, that the set is a member of itself. Then it's not a member of itself, right? Because if it is a member of itself, the set's defined as this containing only sets that are not members of themselves. So if it is a member of itself, it must follow that it's not a member of itself. See that? Because it's a set of sets that aren't members of themselves. So if it is a member of itself, it's not. Okay, then suppose the only other alternative, it's not a member of itself, right? If it's not a member of itself, then it is a member of itself because it's a set of all and only those sets that are not members of themselves, right? See that? So do I need to go through that again? So you have these two possibilities. First is that one is it is a member of itself. Well, then it's not, by the definition of the set. Then if it's not a member of itself, it is a member of itself because it's a set of all those sets that aren't members of themselves. So if it's not a member of itself, it is a member of itself. So the set, if it exists, must both be a member of itself and not a member of itself, which is a contradiction. Therefore, the set can't exist. There is no such set. Okay, but then we can't say that for every group of things, like not being a member of itself, that there's going to be a corresponding set. Because it seems like it's a perfectly meaningful predicate, which we can apply to lots of sets to say that they're not members of themselves, like most sets. Like the set of dogs, the set of cats, all these sets are not members of themselves. Yet there can't be a set containing all those sets that are not members of themselves. So that's like a bad paradox for set theory. They had to come up with a whole new system of axioms in order to deal with that. But I won't go into that. That's more for a course on logic. Russell had a way out called the theory of types, which says basically that you have to stratify your sets and not let sets be members of. You can have sets of individuals, like dogs, and then you can have sets of those sets, and then you can have sets of those sets, but you can't mix like all kinds of sets of different levels together into a single set. So that's how he got out of it. But very few follow the theory of types anymore. They have other ways of revising set theory to get out of the paradox. Okay, now in terms of properties, the problem arises this way. Sets aren't our consideration. You're worried about universals. There's a kind of analog between the two. So how would it work for properties? Well, some properties exemplify themselves. This sort of takes us back to Plato, right, who said that like every property is an exemplar of itself. Like the triangularity is a perfect triangle, and catness is a perfect cat. And, so on. Which led to some problems with like dirty things, which have to like be perfectly dirty, but how can you have dirt and filth and heaven? Whatever. Led to a problem, right? Or a changing thing would have to be like a perfectly changing thing, but you can't have change in the realm of the forms. So there was some problems there. At any rate, some properties are going to exemplify themselves, but not too many. Most properties don't exemplify themselves according to property theory. They reject Plato's idea that that properties are forms, self-realizing perfect forms of things, which cast imperfect shadows on earth, and all the things we see around us for Plato are just these imperfect imitations of the perfect forms. That's been roundly rejected. So according to current thinking, you can have all kinds of properties like catness and dogness and triangularity and redness, and none of these properties possess themselves. In other words, catness is not a cat. It's a quality. As Aristotle said, qualities and cats belong to different categories of being. Right? So cats are substances and qualities are qualities. Those are different, totally separate categories. So qualities just can't be cats, and cats can't be qualities. Cats can exemplify qualities, like furriness, and four-leggedness. And I guess if you add those all up, you get catness, and cats have catness, and whatever kind of view. So what property would exemplify itself then? There are going to be some that must exemplify themselves. So what property most obviously would actually have the very property which it is? The property of... Of property? Yeah, the property of being a property. Good. So the property of being a property is itself a property. So that would be a self-exemplifying property. So some properties are self-exemplifying and some are not. Most are not, right? It seems. So some properties exemplify themselves. For example, the property of propertyhood. Propertyhood is a property had by all properties, including itself, right? Whereas dogness would be a property that's not had by itself. Dogness is not a dog, it's a quality. Dogness doesn't bark. Rover barks. Right? Plato held a different view, as I've said. Plato actually thought that all these forms were sort of actual perfect examples of what they are, which, if you think about it, leads to many absurdities. So Aristotle improved on this and said, no, we have to distinguish the categories. Substance, where dogs and cats belong, is one category, and qualities or properties are a totally different category. And there's a connection between the two. of exemplification or possession of a quality by a particular. But nonetheless, there are some properties that do exemplify themselves, and many properties do not exemplify themselves. So, suppose you take all the properties that don't exemplify themselves, like canininity and felininity and triangularity and hoarseness, and, so on. Right? Leaving aside propertyhood, that weird property that does exemplify itself. Right? Suppose you take all these properties. What is it about all of them that makes them not exemplify themselves? Right? Well, according to realism, you would think it would be the shared quality of being non-self-exemplifying. Right? That would seem to be a property shared by all the non-self-exemplifying properties, like dogness and catness and redness and triangularity. So consider the property of being non-self-exemplifying, which is the property that would explain why all non-self-exemplifying properties are in the same group of non-self-exemplifying properties. Property of being non-self-exemplifying. And so if one were to ask, if one were to say, if one were to say that dogness, catness, and hoarseness are all non-self-exemplifying, there must be something about them in virtue of which they are all non-self-exemplifying. This something can only be the property of being non-self-exemplifying. Therefore, the property of being non-self-exemplifying exists. That would parallel the formal cause argument for saying that dogness exists because Rover's a dog and Fido and Spot. And there must be something about them in virtue of which all of them are dogs. Right? Therefore, dogness exists and so on. Right? But that argument's not going to work in this case, because we can prove that there can't be that property along lines that parallel the proof that there can't be the set of all and only those sets that are not members of themselves. So how would it go? Every property must be either self-exemplifying or not self-exemplifying. Now we take each case. So suppose this property exists and it's non-self-exemplifying. Well, if it's non-self-exemplifying, then because it's the property of being non-self-exemplifying, if it's non-self-exemplifying, it follows that it is self-exemplifying, because it's the property of being non-self-exemplifying. So, right? So if it doesn't exemplify itself, right, then it does exemplify itself. And suppose it does exemplify itself, then it's non-self-exemplifying. So the property exemplifies itself if and only if it doesn't exemplify itself, right? Which is impossible, right? It's got to be both exemplifying itself and not, which is a logical contradiction. It's like something being round and square. So the property can't exist. So here we have a case where things fall into a common group, but there can't be any property, which explains that common group membership by virtue of all the members of the group having that property. So the nominalist can say, "Yay, we can show that there are groups that can't be explained by shared properties." So that's sort of the argument. Do I need to go over that, or do you all see it? It's kind of mind-bending, but if you go through it, you can see. It's not going to work. See, so if it doesn't exemplify itself, then it is an instance of that very kind of thing, which means that it does exemplify itself. And if it does exemplify itself, then it doesn't, because it's non-self-exemplifying. Not the property. A paradoxical property can't exist, so they can't be that property. So what can the realist say, other than just say, well, this is an exception? Well, they can say that, but they need to say more. Don't they need to give some explanation of what all non-self-exemplifying properties have in common? We can't explain their commonality by saying that they share this property. There is no such property. But they still could say, couldn't they, that what they all have in common is not having the property of being self-exemplifying. So they could still give an explanation in terms of property theory. They can say that the property of being a dog and the property of being a cat and the property of being a horse are all non-self-exemplifying because they all lack the property of being self-exemplifying. And that property is perfectly kosher. It's fine. The property of being self-exemplifying gives rise to no paradox. The property that propertyhood has of being a property, of exemplifying itself, doesn't lead to a paradox. It's only the property of being non-self-exemplifying that creates the paradox. So the realist can just say, well, what they all have in common is lacking the property of being self-exemplifying. That explains it. So they don't have to give up and don't have to cry, say, uncle, that we've been refuted just because of this. One might be suspicious in general, in fact, of negative properties, though this is more controversial. Should we admit that there are negative properties at all? If we say in general that there aren't any negative properties, then of course there won't be that negative property. What would be some other negative properties that don't lead to paradox, but which are negative? We might want to get rid of them too for other reasons, like not being an elephant. Think about it. I mean, you can say of many things that they're not elephants. Does that mean we should recognize a property of not being an elephant? Like all these chairs and things, these are all not elephants. But when you say that they're not elephants, how much information are you really giving about them? Like virtually nothing, right? You're not saying anything about what they are in their nature when you say that they're not elephants. Or if you are, it's like minimally minuscule. In other words, you can't explain what something is just by saying what it's not. At least not with any finite list of negative predicates. Yeah, it's not an elephant, and it's not a giraffe, and it's not a horse, and it's not a mountain. Does that tell you what it is? Now, for that, you're going to need some positive predicate, that it's a chair desk or whatever it is. Chair/desk, module, whatever. Right, so you're going to have to say something positive about it. I don't think you can give an account of anything positive in wholly negative terms. You have to use some kind of positive to get at what it is. So it doesn't seem like you lose that much by getting rid of the negative predications, and they seem kind of bogus in a way because they don't really tell you anything about what the thing is intrinsically, that is in itself. They just tell you that it's not some other kind of thing. So that might lead us in general to say we're not going to have negative properties. And then that would give a broader rationale that's not ad hoc for getting rid of this particular negative property that leads to the paradox. The property being non-self-exemplifying. That's the deadly one. Because if you say that there's that property, then property theory becomes incoherent and nominalism must be true. But I maintain that there is a way to explain what all properties that are non-self-exemplifying have in common, is that they all lack the property of being self-exemplifying. So, that would give us an explanation, I think, a metaphysical explanation, without bringing in a negative property. We do it in terms of the lack of a positive property. So anyway, that's what I have to say about the property paradox. So it does help the nominalist a little bit, but I don't think it's a conclusive refutation in any way, or even comes close to a conclusive refutation of the realist argument. Certainly raises a problem that has to be dealt with in some way, but there seem to be some ways to deal with it. Any question or comment on? I lose anybody here? Okay, good. All right, so let's move on to our next topic, identity. So I'm going to take off this stuff here. So we have a blank slate to work on. There is a question. Okay. Yeah.
Negative properties they exist, but they're typically just not used because they give such an minuscule description of whatever you're trying to logically describe.
Well, that's one. Yeah, that's one position you could take. Another position I'm saying one could take is a more radical one, that since they're so useless, that we should get rid of them altogether. Like, why have them? What do we really need them for? Why not just say that the thing lacks this positive property? And then we avoid these really nasty properties that give rise to these paradoxes that threaten property theory altogether, like the property of being non-self-exemplifying, because we can't tolerate that property. So it gives you a more general rationale for why we should not admit the property being non-self-exemplifying. If you say that negative properties are not needed at all, just don't need them. So all properties would be positive on that view. If you do admit negative properties, then your position's perhaps a little weaker. You have to say, well, there isn't this negative property. There may be some other negative properties. This one leads to a paradox, so there's definitely not this one. The property of not being an elephant doesn't lead to a paradox, so I guess technically we could say that there is that property if we really want to. I was just saying there's not really a strong motivation for even admitting that property, since, like, what does it really do for us? And of what use is it to describe things in these negative ways that gives, like, virtually no information about what the thing is like? Yeah.
I know it's from, like, a completely different camp, but couldn't that be seen as just a really heavy critique against, like, Sartre's argument of, like, negation? Because, I mean, he simply says, like, that we understand the world around us by negating everything else and, like, giving particular things, like, meaning. So if you throw into that property, wouldn't it almost just completely level his whole argument that we understand the world that way?
So you're saying Sartre at some point argued that we understand the world through negation?
Yeah.
Yeah, that seems wrong.
Yeah.
Now, I'm not saying that negation can't be used at all to understand things, but it couldn't be that we understand it wholly through negation. That's a non-starter, as far as I can see. Unless you introduce a positive term somewhere in your definition, or unless you have some kind of infinite mind, and you can list, like, all the negative things, and from that deduce that it must be a dog because it's not any other thing, right? But then you'd have to be able to encompass every other thing it's not that's not a dog, whatever, which is impossible for humans to do. Maybe God could do it, who knows? I don't know. Sartre doesn't believe in a God, so that's not the way it's going to happen for him, so, yeah. Right? Yeah. And that's his starting point, right? Nietzsche's God is dead. And the madman in the town square with a lantern screaming at midnight that God is dead. So we start from that. Therefore, there are no wholly objective truths about right and wrong, and how we ought to live, and all. I mean, that's what Sartre concludes from that. Therefore, we should adopt the subjectivist kind of existential standpoint that man creates values and essences, or what must pass for an essence on Sartre's view. Or that, I guess it's not necessarily man, but some kind of mind, some kind of mental entity creates all these values, some kind of finite, non-divine thing in the world, right? Creates all these things. Yeah. In any event, no, it's not. That's not. Yeah, I think that's a good point.
Yeah, it just seems to level his whole argument.
Yeah, I didn't mean to be attacking Sartre,
No,
but I'm happy to see the argument put to
I
that.
just thought it was interesting.
Yeah, no, it's an interesting observation. Yeah. All right, so on to identity. Okay, so identity is a relation that's used in logic and metaphysics. In logic, it's symbolized using this symbol, the equal sign. That symbol is also used in mathematics to express equality, right? Like 2 + 2 is equal to 4. There are some questions about whether that's the same thing as the identity relation or not. We don't have to get into that right now. Point just is that we use that symbol in logic and in philosophy to express strict identity. Strict identity has to do with the idea of numerical oneness. So if you fill out the equation with the equal sign, you're going to have two terms which are going to be said to be identical. So we could pick whatever, like x and y. So x is identical with y. If this is true, what is the case is that x and y are numerically one and the same entity or object. That's the force of identity. So if you had two objects that were exactly similar, but numerically two, like perfect twins, say 2 electrons that are exactly alike, they will be not identical because simply by virtue of the fact that they are 2. In that case, we symbolize that by writing x is not identical with y, or x is diverse from y is a technical term. So this is called, so the contrary of identity is diversity, which implies numerical two-ness, that the x and the y are 2. Even if they're exactly similar, there's still two things as opposed to just one thing, if that makes sense. So that's x is diverse from y. It says that there are two things here. X is one of them, and y is another different object or thing. When you have the identity claim and it's true, you're saying x and y are one and the same thing, even though one of them's called x and the other's called y. X and y are names or variables, whichever the case may be, that refer to the very same item. It's one item. It's referred to as x here, and it's referred to as y over there, but it's the same thing. Just like you could imagine a person who has two names, like somebody who has an alias, or who changed their name. like Kareem Abdul-Jabbar and the basketball player. In his earlier incarnation, he was named Lou Alcindor, so it's the same. So you can say Lou Alcindor is identical to Kareem Abdul-Jabbar, or Cassius Clay is identical with Muhammad Ali. Or Barack Obama is identical with the President of the United States, with the current President of the United States. Does that make sense? So an identity claim will be true if and only if the singular terms flanking the identity sign co-refer. That's putting it in a linguistic way. But identity is not a linguistic relation. It's a metaphysical relation of a thing being the same thing as itself. Right? So that's a metaphysical thing, that anything is itself and not any other thing. That's a metaphysical thing, but linguistically, it's reflected in the fact that singular terms that refer to the thing pick out one and the same object. Next point, identity is considered to be a relation of a very special sort. Most relations hold between diverse things, though not all. So what would be a relation that holds between things that are diverse from each other? Well, the relation of betweenness that I just mentioned. You have to have three things for betweenness, right? You have to have this thing here, for example, this thing there, and then this thing here. It's in between those two things. So my torso is in between my right hand and my left hand. So you have three things there. Betweenness couldn't hold among just one thing, right? You couldn't have just one thing that's like, if X, Y, and Z are all the same thing, then Y can't be between X and Z, right? If they were just one thing. You'd need at least three things to have the betweenness relation hold. That's why it's called a three-term relation. Identity, and then other relations are two-term, right? Like, say, next to, right? So X is next to Y. That means it's right beside it. You have to have two things. So identity is this somewhat atypical relation where you just have one thing that stands in a relation to itself. So that's perhaps a little different than most relations. Most relations, you're thinking of a multiplicity of things that are interrelated in some kind of way. Two or more things. Right? So in the relation of collinearity, you'd actually have an infinite number of points, right, on a given line that are all lying in that line that stand in that relation. So it would be an infinite number of points that stand in the relation of collinearity when they, if and only if they all are in the same line. So there you'd have an infinite number of things. But with identity, you just have one thing standing in a relation to itself. Such relations are called reflexive relations. Relations that things can bear to themselves. Some relations can be reflexive Some relations can be reflexive in the sense that a thing can bear it to itself, but it can also bear it to other things. So identity, though, is a reflexive relation that is necessarily always born by a thing to itself and never to any other thing. Any question about that? So basically, identity is the relation of being of a thing X being numerically one and the same thing as a thing Y, such that X and Y are exactly the same thing. Like Hillary Clinton and Bill Clinton's wife. So one of the properties of identity is that it's reflexive. Everything always bears that relation to itself. So it's a reflexive relation. It's also symmetrical. So to say that it's reflexive is to say that for any x, x is identical with x, making it a reflexive relation. It's also a symmetrical relation, which is to say what? That if x equals, if x is identical with y, then then y is identical with x. It makes it symmetrical. So it's reflexive, it's symmetrical, and it's also transitive. Third property. Which is to say, if x is identical with y, and y is identical with z, then x is identical with z, making it a transitive relation. So identity is symmetrical, transitive, and reflexive. Can we define identity as the unique relation that is symmetrical, reflexive, and transitive? If we could, that would solve the problem of defining identity, right? If it was the only such relation that meets those three conditions, then we'd have a philosophical analysis of the relation of identity, if that was the case. Unfortunately, it's not that simple. Unfortunately, there are other relations other than identity that are symmetrical, transitive, and reflexive. What would be an example of one? Let's see. In geometry, there's a relation known as congruence. So what is congruence? Congruence tells us that if we have two triangles, for example, that if they're congruent, that means that you could superimpose them on one another exactly. It would be a perfect match. So if you have, say, this right triangle, R1, and then one just like it over here, R2, and that these two are congruent, which would say that if you move this one over to here, they would, all the sides and angles would all exactly fit, right? So that relation of congruence, okay, so every triangle is congruent to itself, right? So it's reflexive. The relation of congruence is reflexive. It's also symmetrical. If x is congruent to y, then y is congruent to x. And finally, it's transitive. right? If you have three triangles such that the first is congruent to the second, and the second is congruent to the third, and the first is congruent to the third, so it's transitive also. So we don't have a definition of identity in terms of these three properties of relations: reflexivity, symmetry, and transitivity. So the problem of saying what is identity remains still an open question. Though it's important to note that identity does have these properties, which it shares with congruence. I mean, congruence is kind of an identity-related property because it's basically saying what? That the two figures have the identical shape, right? So it's like qualitative identity, right, as opposed to numerical identity. It's a form of qualitative identity. So any property, I guess, ascribing qualitative identity will satisfy these three things, but it won't be numerical identity. Like color congruence, which would be like having exactly the same color, it would also be, right? Having exactly the same mass, having exactly the same, any of these kinds of qualitative identity properties, say that they have the same property in some respect, will be reflexive, transitive, and symmetrical, but not entail numerical identity of being one and the same thing. So philosophers have tried to come up with some kind of definition of numerical identity. Because if we can't, we'd have to take it as a primitive, undefined relation, which we could do. But it's always better to explain something if you can. Sometimes you can't. So there were various attempts to do this. One is in terms of a principle that was put forward by Gottfried Wilhelm Leibniz, often referred to as Leibniz's law, though this expression is, this title is somewhat ambiguous and may refer to various different principles, which can be, but it can be disambiguated, so there's no problem. Right? Which one you want to be talking about. Some have seen it as an attempt to define identity in terms of property possession. So it's an idea that we can define the relation of identity in terms of the properties that our x's and y's that are identical are going to have. So it's usually broken up into two principles, subsidiary principles, known as the identity of indiscernibles and the indiscernibility of identicals. So let me explain these principles are. So first we have the principle of, Leibniz's principle of the indiscernibility of identicals. Without getting too technical, this basically says for any x and y, if x is identical with y, right, then x has every property y has, and y has every property x has. So it's saying if X and Y are the very same numerical thing, like Hillary Clinton and Bill Clinton's wife, then every property that Hillary Clinton has is had by Bill Clinton's wife, and every property that Bill Clinton's wife has is had by Hillary Clinton. Would that be true? Would it be necessarily true? Seems like it. If they're one and the same thing, then how could they have different? Right? X and Y are one and the same thing. It appears that every property of the first is a property of the second, and vice versa. So the idea is that identical thing, an identical thing, X and Y. People say identical thing, but you really shouldn't. You use the plural because it's just one thing. What's plural is the number of terms that you're referring to, X and Y. Those are two terms, but it's just one thing. So if you want to speak loosely, you can say that if two things, in scare quotes, are identical, i.e. one thing, right, then they'll have all the same properties. There couldn't be any difference in the properties that they have. So if your mind is identical with your brain, then every property that your mind has is a property of your brain, and every property that your brain has is a property of your mind. So, if that's true. So if you turn that around, right, that would mean that if your mind had some property your brain didn't have, or your brain had some property your mind didn't have, like if your brain had the property of weighing 2 pounds, but your mind didn't weigh anything, then that would mean they have to be two different. Your mind and your brain. For them to be the same thing, they have to have all the same properties according to. Just to give you a somewhat more philosophically interesting example than Hillary Clinton's properties. Does that make sense? So a lot of people have said this principle's totally indisputable. However, as is often the case in philosophy, even the most indisputable, obvious principles have been questioned by some philosophers. So actually there are a number of arguments that have been put forward. I think that they're spurious, unsound arguments that have been put forward to dispute this. And we can look at those later. But intuitively, like a priori, if you clearly and distinctly grasp what this is saying, it seems like it must be necessarily true. That if you're just dealing with one thing that happens to be called both X and Y, then the list of properties of X is going to match up exactly with the list of properties for Y, since X and Y are one thing. Right? There are those who question this for various reasons. Elaborate arguments against it. More on that later. We can hold off on that. Now then there's the other principle that Leibniz, so we're talking about Leibniz's laws here, which is the identity of indiscernibles. This one says for any X and Y, if X has every property Y has, and every property X has. Then X is identical as Y. Let me explain first how Leibniz understood this principle. Leibniz only recognized certain properties as falling within the scope of the principle. The properties had to be expressible in wholly general terms. In other words, they had to be expressible without using names or other similar singular terms. So for example, you could talk about red as a property of an object, or being a wife or a husband, but you couldn't use properties that contained alleged properties, putative properties, that contained a name of something. Say the property of being identical with Hillary Clinton, or being next to the Statue of Liberty. The properties had to be expressible in purely qualitative or purely general terms. The properties could be either intrinsic or relational. So you could have the property being red, which would be a general intrinsic property, or the property being round, or furry, or whatever. These would all be general intrinsic properties. A non-general property is a property that you need to use a name to express, like being next to that wall. But the property being next to a wall would be okay, because that's a general property or relation. So Leibniz was willing to allow in here reference to, as properties, any intrinsic or relational general property or relation. So his claim was that if X and Y have all the same general properties and relationships, then X and Y must be numerically one and the same. That's how Leibniz understood the principle. Understood in that way, the principle is highly controversial, unlike the first one, which is seems to be self-evidently true, even though even it, as I've said, is controversial. But I think for bad reasons, or reasons that can be satisfactorily answered. Second principle, though, is much more dubious, understood in the way Leibniz understood it. And the reason being that you might have a universe containing two or more things that are exactly alike. So if you had two things that were exactly alike, like perfect twins, they could have all the same general properties and relations and yet not be identical because they'd be two different things. In order for that to occur, not only would the two things have to be exactly similar intrinsically in themselves, but they'd also have to be symmetrically arranged such that they didn't have any different relationships to anything else as well. But even that can be met in a number of ways. We can imagine conceive or imagine possible worlds where you have a number of objects that are numerically distinct but exactly alike. Internally, like electrons, not only internally but also in terms of how they're related to other things. the universe would have to be completely symmetrical in order for that to occur. I can give you some examples of such universes fairly easily, but if those worlds are possible, and they seem to be, the identity of indiscernible things is not necessarily true. You could have things that are indiscernible by their properties, but yet are different things. Leibniz's argument for his principle of the identity of indiscernibles was based on two principles that are not universally affirmed anymore, though he thought they were very plausible. One of them is the principle of sufficient reason. This is how Leibniz argued for this identity of indiscernibles interpreted in the way that I've stated. He said, first of all, the principle of sufficient reason is true, which says that everything must have a sufficient cause for why it is rather than not. There must be a sufficient reason for anything that exists as to why it exists rather than not existing. And the second principle had to do with the existence of God. He argued that the universe was created by a supreme, perfect being, so that the God of traditional Western theism exists, the God who is omniscient, and, omnipotent, and morally perfect, and eternal, necessarily existent, and so on and so forth. There is such a being than which none greater can be conceived, or than which none greater is possible. And Leibniz argued that given the existence of such a being and the principle of sufficient reason, we could show that there couldn't exist a world in which there were two indiscernible things. Why? Because basically there couldn't be any sufficient reason for God to make a world like that. Like, why would God make a world like that? Well, he argued like this: suppose you have a world containing nothing but two spheres, and those two spheres are exactly the same. Same diameter, same weight, same everything, right? And they're perfectly spherical, so one doesn't have a bump there. There's not like a crack on this one. They're exactly the same, right? But of course, one would be here and the other would be there, right? They'd be in two different places. But he argued that would violate the principle of sufficient reason for God to create a world with two such spheres. Because God could have no sufficient reason for putting this sphere in this place as opposed to being in that place, because it would make no difference, since they're exactly the same. It could make no difference to the value of the world, whether this sphere was here or whether it was there. So having them interposed one way or the other would not affect anything that could be a sufficient reason for God to choose between one world or the other. So we concluded that any two worlds that God might create would have to differ in some way. Really differ. Not just differ in the fact that in one world you have something that's indiscernible from another thing in a different place, but actually differ qualitatively. Like this one's got a bump on it or a crack in it. Or at least it's differently interrelated. At least the things are related differently in the worlds. If you just had two things, though, right, and nothing more, then it's hard to see that there'd be a difference between having them arranged this way as opposed to that way. That one make no difference. So that was Leibniz's argument. I guess the big weakness in it is that, A, you have to assume that God exists, which is not a universally accepted proposition anymore. It seems very difficult to prove it using purely scientific or philosophical principles, as David Hume argued in the famous Dialogues on Natural Law. also seems like there's no consensus that you can prove the existence of God a priori via the ontological argument, which says a supremely perfect being must exist, because if it didn't, it wouldn't be as perfect as if it did. That argument's widely regarded as circular and pretty useless. So if you can't prove that God exists, that's one problem for this argument. The other problem, of course, is the principle of sufficient reason has also fallen under doubt due to quantum mechanics largely. In quantum mechanics, they came to the conclusion that it doesn't have to be a sufficient reason for the occurrence of a subatomic event. That subatomic events occur sort of randomly without any sufficient cause. So a particle just might pop into existence at a given time or place or not, and there's no sufficient cause for why it would do that. The best you can say is that there's a certain probability to do that or not, but there's no actual fact of the matter that determines what will occur. So given that both of those assumptions of Leibniz's have come under severe questioning, and given that it seems possible to imagine worlds in which you have two things that are exactly alike, it's hard to affirm the identity of indiscernibles as a necessary principle. Given that, it doesn't seem like we can define identity in terms of the conjunction of the two principles. I mean, that was the hope, that we can say in general, and this is often referred to as Leibniz's law, that x is identical to y. For any x and y, x is identical to y if and only if, right, x has every property y has, and y has every property x has. So that's the LL principle for any x and y. X is identical to y if and only if, which we give you a definition. X has every property. Y has, and y has every property. So the basic objection to this identity of indiscernibles is you could have a world with two indiscernible objects, like these two spheres, are exactly alike. And if there's nothing else, it's hard to see what the difference is. Well, it might be said there still is a difference in terms of direction, actually, to be really technical about it. If we can call this sphere here, make it a little bigger so it's the same thing. This is sphere 1 and sphere 2. Right? If we just pick any point in here as our point of origin and create a x and y axis, doesn't matter where we pick it. We can then define directions, like positive and negative directions, given that point of origin, and creating an x and a y axis. Right? In ordinary language, it would be like eastward and westward and northward and southward. Right? So I'll just stick with that. See, sphere 1 has a sphere to its what? To its east, yes. Sphere 1 has a sphere to its east, right? But it doesn't have a sphere to its west. Whereas sphere 2 has a sphere to its west, but not a sphere to its east. So it looks like there is a discernible qualitative difference between the two? It's like a defense of Leibniz. Right? There is a qualitative difference. If you allow directional properties, qualitative directional properties, and there seem to be inevitably such properties. And you get to pick your point of origin for free. It could be anywhere. It doesn't matter. You still get the same result. It's just an arbitrary choice of a point. You set up your directional framework. The way out of this, though, the answer to even this retort, though, is you just need to multiply the number of spheres you've got. So we now imagine, instead of just two exactly similar spheres, a line, right, on which you've got an infinite number of them in both directions, passing through this. They're all centered on this line, and they just keep on going. You get another one there, or on this side. Right, so now there won't be any difference in these directional properties either. Every sphere will have a sphere to its east and a sphere to its west. And they'll all be exactly the same. So Leibniz still loses. Still turns out that you can have multiple qualitatively indiscernible objects. Another possibility would be to use Cartesian souls that aren't located in space. Leibniz believed in the possibility of those things. He called them monads. So if you have all these souls, they're not in space at all, right? Then they could all be exactly the same in their mental states. You could imagine the possibility of psychological twins, exact psychological twins. They're not anywhere, they just all exist. So autonomous mental beings. Then there'd be no way also of distinguishing them in terms of their properties, given the way Leibniz understands properties. So it doesn't look like Leibniz's law combining these two principles can be used to define identity either, because of these difficulties with the identity of indiscernibles. So next time I'm going to turn to some of the supposed objections to the indiscernibility of identities. And also distinguish it from another very similar principle that Leibniz defended, which it should not be confused with, called the principle of unqualified substitution, which says that if you have two sentences in which you have two co-referring singular terms, like Hillary Clinton and Bill Clinton's wife or whatever, that you can always substitute one term for the other without affecting the truth value of the sentences in which they occur. This is a principle which is closely associated with the indiscernibility of identicals principle. But as we'll see, because it's a linguistic principle, there are some problems that it faces that don't seem to affect the metaphysical version. So we'll talk more about that. Principle of unqualified substitution, salva veritate. What that means is that you can replace the term, substitute co-referring terms that refer to the same thing without affecting the truth value, while preserving the truth value of the proposition, not having a switch from true to false or from false to true. We'll see that there are some serious problems for the linguistic version of the principle. And we'll have a look at the metaphysical objections that have been raised to the indiscernibility of identical principle as well. Okay, so I'm giving you to Monday to get that first essay exam in, and I'll see you all on Tuesday. Are you all aware of the paper this afternoon? There's a paper being given at 5 o'clock on drug policy, a paper in ethics. It's at 5 o'clock.
It's in education, but I can't remember what it
224. 224.
SOEB 224?
Yes.
Yeah.
Nailed it. You said it.
Yeah, so He's a philosopher of law from Rutgers University, which is considered like the top university for graduate students in philosophy. You're all welcome to attend. I'll be there.
Oh, is it? Okay.
He